Okay, and welcome to our informal-ish discussion of multivariate methods, multivariate statistics. Um, and it's going to be an informal kind of introduction to it. I'm even wearing my hat to show how informal and casual it's going to be. Plus, I'm wearing my hat because I'm doing this in the evening, and with the light here, I would probably blind you with my head. And so we'll just keep that on, and we'll be all good to go. So multivariate. Why multivariate? Well, I'm sure everyone that's watching this has seen at some point multivariate plots, whether they be PCAs or NMDS or whatever it might be. And I thought that it might be handy if we kind of looked a little bit behind exactly what these methods are doing and, more important, how to interpret them. And so multivariate analyses are simply analyses where we are interested in modeling data or describing data where we actually have more than one response variable. So the majority of statistical approaches that we're covering in this class, for example, there's a single response variable, right? We maybe want to make a model where we are going to predict the height based upon some kind of predictors, but that thing that we're trying to predict is a single response variable. Multivariate analysis, as the name implies, is where you have multiple things that you're interested in describing and ultimately perhaps predicting. And so we call that multivariate. And there's two main kind of groups that you can think about with multivariate statistics. One is used as an exploratory method to understand the variation of your data, or just to simply describe it. And so these would be methods where there's no explicit hypothesis testing happening. It's just a way to describe complex multivariate data. And so these would be things like principal components analysis and principal coordinates analysis and correspondence analysis and non-metric multidimensional scaling. Then the second group are ones where we can actually do hypothesis testing on it, and we will talk a little bit about some of those in a few weeks, hopefully. And those would be things like redundancy analysis or canonical correspondence analysis and things like that. But we're going to just explore a few methods so we can get an idea of what's happening behind the scenes and how to interpret and implement these methods for your own research, as well as to understand when other people are presenting multivariate plots that we have an idea of how we're going to interpret basically those results. And so the first one that we're going to talk about is called principal components analysis, or PCA for short. And it can be really helpful with high dimensional data. So, for example, let's say that we had 30 different variables. So we measured 30 different aspects of something, or we took 30 different types of measurements of something. So, like 30 different measurements, it might be maybe you're looking at soil, right? And you're thinking about water content, salt, the amount of nitrogen, the amount of phosphorus, and you could get a lot of different things that you could potentially measure about soil characteristics. And so it can start becoming pretty cumbersome if we were to just look at a bunch of correlations among all of those things. So, for example, if you had 30 different variables that you measured, I think you would have 435 different possible correlation plots that you would potentially be interested in looking at. And that's kind of wouldn't be very helpful, especially since those would be just a bunch of pairwise correlations, and we wouldn't be able to account for the fact that all of those different things might co-vary with other things differently. And so this is where principal components analysis comes into play. And basically, the goal behind principal components analysis is to take this really highly dimensional data and capture as much information as possible with the fewest number of descriptors. So again, instead of having 435 correlation plots, it might be useful if we could reduce that down to maybe 3 or 4 things that we're actually interested in looking at. And so how it works conceptually is, and this is going to be totally conceptually, is imagine over behind my shoulder. Look at that. Jim's prepared. Let's say that you have just a bivariate situation here, blinded by the light, where you have, your first variable and your second variable. And obviously, when you only have 2 things, we could just simply make this bivariate plot, maybe calculate the correlation, go home and feel good about ourselves. But obviously, we're going to be talking about situations where we have way higher dimensionality than just 2 dimensions. But conceptually, we can think about this with 2 dimensions. As a kind of a cartoony way of thinking about what principal components analysis is doing is it's going to set up think of it as a line through the data that maximizes its ability to capture all of the variation that's here. And so that first line might be something like this. Okay, so that looks like that's doing a pretty good job at maximally capturing all of that variation. And so we might call that PC1. This is going to be principal component 1. And then once we have that first line, we're going to come up with a second line that's going to be orthogonal to the first line. And so what orthogonal means is that it's going to be at a right angle to this first line. And now we're going to try to find the best line that captures the maximal amount of variation that's orthogonal to this first axis of variation. And so here, again, this is all cartoon. So I would do something like this. Okay, so now I put those 2 lines through this 2-dimensional data. And then if we were to look at the PC plot of this, the principal components analysis plot of this, it would basically look like this. This is what you would put in your PowerPoint and impress everybody at your talk. It would look kind of like this, except, how's that for high tech? It would look like this, right? And that would maybe be your PC plot of that. God, that was miserable. Okay. I usually describe this as like a 3-dimensional problem. If you imagine a cloud of points, and what you're trying to do is you're trying to find the axis that could go through that cloud of points, and then a second axis through that cloud of points. And then in this case, we're dealing with 3 different dimensions, right? And so you would have a third axis that would go through all those points. And so that's conceptually what the principal components analysis is going to try to accomplish. And the point behind doing that is instead of saying, oh, we got variation for our original y and our original, or our first original variable and our second original variable, by doing this, we can now maybe say that principal component 1 is actually explaining maybe about 75% of the total variation, and principal component 2 is explaining 25% of the variation. And so all that principal components analysis ultimately is doing, and it's actually called this, which is why I decided that it would be dramatic if I rotated this actual whiteboard, which really failed miserably. But it's basically just a rotation of the data. We're just kind of rotating it until we can capture most of the amount of variation on the various axes. And so the cartoon of the cloud and thinking about 3 lines going through the cloud that's capturing maximal amount of the variation works great as long as we have 3 things that we're interested in, right? We, as humans, we're pretty good at thinking in 3 dimensions. But if we go back to that initial example, if you had 30 variates, it's really hard to get your head around what 30-dimensional space looks like, and that's why we do the math, or we have the computer do the math. And behind the scenes, there's a lot of, basically there's a lot of matrix math that's going on, where we are going to decompose the variation in the data. But what we're going to do is we're going to just go through and let's think about how we're going to interpret these analyses so that we can understand what we're exactly getting out of a principal components analysis and how we can, interpret it so that way we could make some biological inferences or at least refine what our intuition is of our understanding of the natural world. I will say one good follow-up book, there's actually two, but this book right here is freely available at the libraries as part of their ebooks. It's actually the earlier edition of this, but principal components analysis hasn't really changed much in my lifetime. So this book has a really nice chapter on principal components analysis. Trust me, I held that up and it's blurry, I know, but it's a chapter in here that includes principal components analysis. And it's actually a very readable book that explains maybe in a little bit more mathematical detail what's happening behind the scenes. And if you're really enjoying that, the big version of numerical ecology, it's a big one, it's like a phone book, has an entire chapter of lots and lots of pages on principal components analyses, as well as some of the other multivariate analyses that we're going to talk about. So ultimately, what we're going to want to end up with for each of these axes, it's going to look a lot like a linear model looks. So for any given individual, which we can call Z1, okay, that's going to be sample one that I've taken these different measurements from. We're going to construct a model that is going to capture the variation that is explained on principal component 1. And so if we're talking about, well, let's just think about principal component 1. And so we're going to have these coefficients that, say we had our two different variables that we were putting in there, x1 and x2. So maybe it's, I don't know, I always say length and width, but it could be whatever you want it to be. Oh, maybe it's soil phosphorus and soil nitrogen. I'll stick with the biological ecosystem theme. And then we have these coefficients here. And I probably could write this as 2, 1. So this would be some value, and you would take that value and multiply it by the observed value for whatever individual had for, say, phosphorus, plus some other coefficient times the value that that first individual had for the covariate 2, so maybe nitrogen or whatever it might be. And that would give you a score for that first individual for that first PC axis. And then you would do the same thing again, where you would have the same thing happen with the second axis here, where you would have, it would look something like this. Where this would be how you would calculate the score for the second axis, and then that's what's determining where your little dots are going when you're making a PCA plot. Okay, it's a function of these things, and what we're going to get into in a second here is where do you find these coefficients, and how do you interpret them, and these coefficients can make up what's referred to as an eigenvector. So as I said, a lot of the math behind the scenes of what's going to be happening here is a lot of fun with matrices. And maybe some of you have taken matrix math classes and you're familiar with the concept of eigenvalues and eigenvectors. Simply, we can think of it for our purposes as a way that we are extracting information from a large matrix. And in our case, what it's going to end up being is we're going to be interested in understanding the variation among the different predictors on how they covary with one another. Okay, so I think that PCA is one of those things where it's actually easier to understand if you just play with it, because I don't feel like putting together a really long mathy talk. Okay, so, oh, hey, look, that's exactly what Jim said. Look at that. Here we have it. Okay, so we're going to start with just some play data. And let me name the rows and the columns, and we can look at the play data. So let's say this is our play data. So this is a two-dimensional example. Again, you would never really do principal components analysis if you only have two covariates, because you could really simply just look at the covariance itself and not bother with any kind of inordination. Although it's kind of fun to turn the whiteboard on an angle. And so what do I have here? I have cooked up some ideas here. We have 6 individuals, cleverly numbered, individual 1 through 6. And then I've taken 2 measurements. And you can pretend that they are your favorite measurements, whatever they might be. Length and width, phosphorus, nitrogen, whatever you want. I get a kick out of it. And so there are a number of ways we can do principal components analysis in R. The simplest one is to use a built-in function called prcomp. And if I were to type in $prcomp, you can see it's part of the base stats package. Everybody that's watching this that has R on their computer, you have this on your computer. And what you can see is what it wants is, let's just focus in on this first thing here, X. And X is just simply going to be a matrix or a data frame, a matrix-like object, which is exactly what this is right there, right? That is a matrix-like object. The values itself are just the numbers, okay? I've put the individual 1, individual 2, so on. Those are the row names, and then the M1 and M2 are column names. And so here we have our data that are in there. And I am going to create an object called as prcomp, because this is going to be an object that's created by the prcomp function. And all I'm going to do is I'm going to say, I want a principal components analysis, please. And I want it on my data, which I call DATS. And so I go ahead and I run that. And what do I get? Well, and this is where things can maybe be vague. Like, what are we talking about here? So what we have here, these are what are referred to as the eigenvalues. And they are presented in units of standard deviations, which means that if we were to take the square of them and add them together, then we're going to add together it as units of variance. So right now it's in units of standard deviations. We all know that the standard deviation is simply the square root of the variance. So if we wanted to know what the variance was, all we would have to do is square that term. And so if we were to square both of those and add them together, we get 7.661665. That value happens to also be the variance of our first column. So the variance over here of these numbers, and plus the variance of this column. And if I add both of those numbers together, I get 7.661667. So again, if we go back and look at our principal components analysis, if we were to square these two things and add them together, that is going to equal the total variance that is in the that are in our data. And so once we understand that these are in unit variance, we can start to think about how much of that, all of that variation, is being captured by the principal components analysis. Here we have 2 axes in the principal components analysis because we only had 2 covariates. And we have the first axis. This is the eigenvalue associated with the first axis. And this is the second axis, which is going to be reflective of the amount of variation captured by the second axis. So one thing I'll point out here is that you'll notice that the second number is smaller than the first number. And if you remember when I did my little cartoon up here, I said that the first PC was going to try to maximize the variance, right? And then the second axis was going to be orthogonal to that. So we can think of that as it's capturing all the variation that wasn't captured by the first axis. And in this case here, all we have are two predictors. So we have two eigenvalues. And again, if we add the square of these together, it's going to equal our total variance. And so the first axis is explaining more of the total variance than the second axis. And we can even figure out what that would be, right? So we know that our total variation is 7.661667. So if I were to take that value and square it, okay, so now that's in variance units. And if I was to take that value and divide it by the total, we would say that that first axis is explaining 72% of the variation, which means that the next axis must be explaining somewhere around, math in my head, 28%. How's that? Good work, Jim. And so we can even prove to ourselves that maybe Jim is okay doing arithmetic in his head, which is always a risky thing to do. Copy, paste. Yeah, 27.93% of the variance. So one thing to point out here is that we've lost no information. All of the information is still in there when we think about the total amount of variance that is in our data, but we've rotated it in such a way that the first axis is now explaining 72% of the variation, and the second axis is explaining 27.9% or 28% of the variation. And so that's what the eigenvalues are telling us. They're telling us something about how important each of those axes are when it comes to explaining the total amount of variation. Oh, look at that. I did it. See? That's exactly what I did. So all the variance is accounted for. And so now we can start to think about what's the relative importance of measurement 1 versus measurement 2 when describing what each of those axes are explaining. And this is what is referred to as the eigenvector. So if we go back up to our PCA object, okay, right here is our eigenvector. Okay, so these are the eigenvalues. They tell you something about the magnitude of that axis, and then the eigenvector tells you how important measurement 1 and measurement 2 is for describing that variation that is explained on PC1. And when it comes to interpreting this, we're interested in the magnitude of the value. The signs don't matter when we're thinking about the importance. What matters is the magnitude. So you can think of it as the first thing you want to do is you look at those numbers and you can go ahead and you can take the absolute value of those numbers. And 0.98 is greater than 0.18. And so PC1 appears to be dominated primarily by our first measurement and the second measurement isn't quite that important. Whereas PC2, remember that's the orthogonal axis to that, measurement 1 isn't very important and measurement 2 is really important. So again, both of those measurements are getting their fair share of speaking time, if you will, except PC1 is 72% of the variation and it's dominated by the first measurement. PC2 is only 28% of the variation and it's dominated by measurement 2. Okay, how do we think about the signs? So the signs tell us for that particular axis how those two measurements co-vary with one another. And so on PC1, which again is explaining 72% of the variation, it's dominated by the first measurement. Second measurement isn't terribly important, and they negatively co-vary. And so remember, covariance is, how things rise and fall together. And the fact that we have something with a negative here and a positive here, that means along that axis, we have a negative covariance between measurement 1 and measurement 2. When we go to PC2, they are both positively covarying with one another, which means they are rising and falling together, and that's explaining 28% of the variation. So we could step back and we could say, okay, well, for 72% of all the variation that's in the data, measurement 1 and measurement 2 are negatively covarying with one another. For the remaining 28% of the variation that's explained by PC2, now measurement 1 and measurement 2 are positively covarying with one another. Now, if you go online and you look for helps on PCA, I just want to give this warning. So PCA is used a lot in I froze. Man, I hate that. Let's try that again. Yeah, I'm gonna quit that. Let's do a new movie recording. You guys are seeing all my top secret tricks. And then I will say that I want it to float on top. And then I will make myself small again. There we have it. Okay. Right. So one thing that I will say is that when you're going and exploring online for help, or even when you're reading papers sometimes, PCA is used frequently in morphometric analyses. So, people will have like 50 different measurements of a fish skull, or, 50 different measurements of something, of a tree. Doesn't matter. Oftentimes what happens when you're doing these types of analyses and you're collecting real data, especially if it's morphological data, is that the most important component of the variation ends up being size. And if size is overwhelmingly an important axis of variation, what will happen is that it'll be captured by the first PC axis, and all the signs will be the same, okay? And usually positive, but they don't necessarily have to be, but usually positive. They'll all be the same is the key thing. And so if they're all the same, what that implies is that whatever those measurements are, as one's getting bigger, the other is getting bigger, and they're all getting bigger. And so a lot of times you'll hear people say, well, the first PC axis is size. And that often is the case, but that's not necessarily a rule. What different signs would tell you if you have strong loadings of positive and then you also have strong loadings of negative, that's usually telling you something about shape variation. And you can think about that as, if one thing is getting bigger while the other thing is getting smaller, that's going to change the shape of it. Kind of like you're squeezing a balloon and it's changing the shape. As opposed to if it's just size, then everything is kind of getting bigger and smaller at the same time. So I just wanted to mention that if you're exploring online and you're thinking about more like, how about a different way of explaining PCA to me? That's totally fine. I encourage you to do that. There's a lot of helpful resources out there. Just be aware that there is a culture of assuming that PC1 is always size, and that's not necessarily always going to be the case. It just happens that it's often the case. So I just wanted to mention that. I'll also mention that this eigenvector here is also referred to as loadings. And without going into some kind of a pedantic argument, technically they're not loadings. They are the eigenvector. Loadings is a term that's borrowed from something that is somewhat similar to this called factor analysis, where they actually are loadings. But just kind of be aware that you might or might not see them be referred to as loadings, or here they're referring to it as the rotation, or it could be referred to as the eigenvector. I know that JMP, the jump software, at least last time I used it, called them loadings. And I believe SPSS calls them loadings. But you might, there are enough pedantic people in the stats world that they might yell at you if you call it loadings. But for our purposes, I'm totally happy calling it loadings. I think we should just call it loadings and not care what the other kids say. So, what can we do with this? Let's go back and look at I already have it up there, our PC object. So there we have it. We have our PC. We understand what the eigenvectors are telling us. The eigenvectors are telling us something about the magnitude of the importance of the different PC axes. We know that we can take those values and we can square them, and then they will be in units variance. And we know that the sum of those would be the total amount of variance that is in the in our principal components analysis. And we understand how to interpret these eigenvectors, right? The loadings. So again, M1 is very important on PC1, and M2 not as important. And then once you get to PC2, M1 not so important, M2 pretty darn important. Right. And so what can we do with that? And let's try to understand what how we could calculate what our scores are, right? That Z1, like we want to figure out the scores. So the first thing that we need to appreciate is that, recall that when we're doing, because behind the scenes, the PR comp function is doing the whole matrix decomposition based upon the covariance matrix. And remember that when you're doing a covariance matrix, that you are basically looking at the difference from the mean for each individual, right? How different are you on X minus the mean of X and Y minus the mean of Y? And so if we want to kind of delve in and think about where our scores are going to come from, we're going to center all of our data. And we can do that using the scale function, which we've used before. That's going to Z-transform the columns. And the scale function has two different arguments that are by default true. So it's saying center my data and scale my data. So this is going to center your data at 0, and then you're going to divide it by the standard deviation, and that's going to give you your Z-score. But since we're going to be dealing here with the covariance matrix, at least for this moment, we're going to be dealing with the covariance matrix, I'm going to add in this extra argument, which is scale equals false. Okay? And so all that's going to do is that's going to center the data. And so we can look at this, and now we can see that if we look at our raw data, let's start with our raw data. Here's our raw data, right, that we put into the PR comp function. And then if we look at the centered data, this individual here, individual 1, which was 3.1 for measurement 1, 3.1 is 0.9 less than the mean across everybody for measurement 1. Okay, so all we've done is we've centered our data at the mean. So now the mean is going to be 0, and this one is 2.8 greater than the mean. This one's 1.9 less than the mean, 0.7 less than the mean, 3 greater than the mean, negative 2.3 less than the mean. And so now we've centered all of our data. So we have those values, and now let's go back up to our PC object, which is right here. It's always convenient when I point, I know. And now we can go ahead and we can pop it into this simple formula. And so I'm going to take the loading, if you will, the value in the eigenvector for measurement 1, which is 0.9831247, and I am going to multiply that by the observed value, which is negative 9, right here. And then I'm going to add to it the second value in the eigenvector, which is negative 0.1829367. So here that is right here. And I'm going to multiply that by the observed value for measurement 2 for individual 1. Okay, so all I'm trying to do is figure out what the heck is the PC score for axis 1 for individual 1. And if I do that, I get negative 0.4122258. Okay, so that's the PC score for individual 1 on axis 1. So you would never do this by hand. Please don't ever do this by hand. That would be such a cumbersome mess for you. If we look at that object that we created when we used the PR comp function, and it's just say names, it actually returns a list. And one of the things in that list is this little x. And so if I were to pull out the values that are present there, it's going to give me the PC scores for all of the individuals. And you'll notice here that the score for individual 1 for PC1 is minus 0.412258, which is the exact same thing we got when we did it by hand, right? I always find it satisfying to do things by hand because I don't like things being magic, which kind of makes me sound boring, but I don't like things being magic. And maybe I am boring. Look at me. And so within that PR comp function, or within that PR comp object that we created, the scores are in there. An even easier way to extract the scores is simply to ask for them. We could use a function called scores, ASPRCOMP, and there we have it, right? We get the exact same things. Okay, so now we can look at a plot of our data. Now we have the scores, and we can see what that plot might look like. So I'm going to make this bigger so I don't get yelled at for not having a big enough plotting surface. And I am going to say, I'm going to plot the scores of our PC object. And they look something like this, okay? So here's PC1. Remember, PC1 is explaining, what was it, like 72% of the variation. And then here's PC2, which is explaining the remaining 28% of the variation. And these are our data projected into PC space. And we could compare that to, let me do this real quick. I'll make a little quartz window. And I'm going to plot them side by side with our raw data. And so let me do a little chicanery here. Parameter mfro equals 1 row, 2 columns. That's just a little bit of chicanery to make it plot two things on the same plotting surface. And then I'm going to go ahead and here's our raw data, which I will show you in a second. And then that is our PC data. And now I will take the mystery away and put it here. Okay, so here's our raw data. Here's our PC plot. Now, the first thing you'll recognize is that the plots look incredibly the same. They're not identical, but they are incredibly the same. And the reason why they're incredibly the same is because we're doing a principal components analysis with only 2 variates. As I said, you would never do that. You could just look at your data by plotting it. But, you know, simple is always a good place to start. But I will point out that here, this PC plot, what you can see is that it is quite literally rotated a little bit, just like I did with the whiteboard when I almost made a mess. And again, recall that the reason why it's rotated just a little is because the first PC axis is dominated by M1, right? It is super dominated by M1 and ever so slightly M2. And so what it's doing here is it's just rotating it just a little bit to account for the fact that PC2 gets to own a little bit of this, not much, but it gets to own a little bit of the variation on this axis. And so it's just being rotated in such a way that we can basically understand the overall makeup of what our data look like. And then again, PC2, same thing. So they look really similar to one another, as they should, because we only had 2 covariates in our PC analysis. Okay. And so let's see. What did I say was a good? Aha. So another way to do the exact same thing is to use a function that's in the vegan package. And I'm going to show these functions in the vegan package because the vegan package is a really nice tool set for doing ecological work, and as an extension, it's a really nice toolbox for doing multivariate ordinations. And so it's called vegan because it was originally written basically to do analysis of plant community data. So they called it vegan, which was, cute. So we got vegan now loaded into our workspace. And there's a function that we can use within vegan to do a principal components analysis. And that function is going to be called RDA. And RDA stands for redundancy analysis. And when we talk about constrained ordination, which is ordination where we're actually doing hypothesis testing with a multivariate method, one of the methods we can use is called redundancy analysis. But if you just put your raw data into the redundancy analysis function and you don't give it any constraints, meaning you don't tell it to account for certain things for hypothesis testing purposes, the function RDA will give you a PCA. Right. And so here I'm going to create an object called using RDA. And I'm going to just say RDA, and then I'm going to just put our raw data in there. And again, this is our raw data, so I'm going to do that. And then I say a summary. And now notice that, it's giving us scores, it's giving us eigenvectors, and let's go up to the top because there are some minor differences in how it's presenting the data. So how the RDA function is going to represent the eigenvalues here, it's going to show them in units variance. So recall that when we did it using the PR comp function, it gave it to us explicitly as standard deviations. Here, the RDA function is giving it to us in variance, and they call it here inertia. And you might recognize that 7.662 because that was the value we got when we took our results from here. When we took these values and squared them. So if I take that and I square it, and I take that and I square it, and then if I go back down here, oh gosh, I'm starting to get dizzy. Right, here's the eigenvalues that it's giving us. And notice that the first eigenvalue is the square of the first eigenvalue from the PR comp function, except now it's in unit variance, so it's 5.52, and then it's 2.1405. So it's the same thing that we get. We just need to remind ourselves what units these things happen to be in. Right. And then we've talked already about where this proportion explained is coming from, right? So we know that the total is 7.662. That's the total variance that is in our data. And we know that the first principal component then is explaining 72% of the variation because 5.5211 divided by 7.662 equals 0.7206. Okay. And the same arithmetic applies here for the proportion explained by the second axis. And then notice that they have the cumulative proportion. So once you get to PC2, you've explained 100% of the variation. Because again, you lose no information with a PCA. You just maybe choose to look at parts of it at a time, but you're not losing any information when you do these ordinations. So the scores that you get out of the RDA function are slightly different than the scores that we got when we did it using the print com function. So scores, I'm going to do it this way because otherwise I'm going to get lost. So where did we do that? Scores, right? Here's our scores. Okay. Notice that the scores are different. Okay. And also notice that our loadings, if you will, are different. They're different because the RDA function is scaling things slightly differently. And we'll get to the point in about 3 minutes here where I show you that it really doesn't matter, depending on what you want to do, but it doesn't matter. They're scaled, but they're scaled by a constant. And so they're going to be perfectly correlated with one another. But the scores themselves are going to be different. So just be aware of that. But at the same time, it's always important to remember that the actual values here in PC land don't necessarily matter as much as the distance between these points. That's the thing that's interesting, right? Like in PC land, these two guys here are really similar to one another, and this guy over here is way off by himself, and these two guys are similar to one another, and so on. Okay, and so the scaling is going to be a little bit different when we use the RDA function. And further, there are a number of different types of scalings that you can do on the scores depending on what you want your plots to look like. And so what do we mean by that? Seems like a good thing to ask. So first, let's just think about using that summary function. And so if I were to use the summary function and I were to do a summary on that object that I created with the RDA function, and I said scaling equals 0, that's going to do no scaling at all on my scores, on my site scores. Okay. There still is a constant behind the scenes that is going to affect it, so they're not going to be the exact same values as if you use the PR comp function. But the site scores themselves are entirely unscaled. And so, yeah, let's hold that thought. The next type of scaling is called scaling equals 1. And what that does is the scores themselves are going to be scaled by the sites. Okay? And how that would be informative is if we were to look at what's called a biplot. And so now let's look at what a biplot is so we can start to interpret this. Okay. So this is what's referred to as a biplot. Here we have all of our points, right? Individual 2 and 5 are right next to each other. 3 and 6 are right next to each other. And we have 4 and 1 that are kind of doing their own thing. And then we have these arrow plots. Okay, this is what's referred to as a biplot. And you'll notice it says M1 here and it says M2 there. So the scaling, the fact that I said scaling 1, what scaling 1 results in is a situation where we can trust these arrows, but the distance between each of these individuals is ever so slightly being distorted, because when you say scaling equals 1, that's usually when you want to interpret your different covariates, your predictors, if you want to think about it that way. Here being measurement 1 and measurement 2. So let's start with how in the heck do you interpret this in the first place, which I think is a very legitimate question because they tend to be confusing and they tend to be everywhere. So how do we interpret those? Here is PC1, okay? This dotted line here is centered at 0, and that's where we're starting this here. What you can think of is how parallel either of these arrows are to PC1 will tell you something about how important that particular thing is, or how strongly it is correlated with PC1. And remember when we were thinking about the loadings, that M1 was loaded really heavy on PC1. Okay, and notice that it's really, really parallel to it. So it's strongly correlated with it. And then you'll also remember that the magnitude of M1, right, was big. And its bigness is reflected by how long the arrow is. And so just looking at this biplot here, you could look at this and say PC1 is dominated by M1. Whereas if we were to flip our heads around and look at M2, M2 is parallel, much closer to being parallel with PC2, right? And it's really long. And so it is heavily loaded on to PC2. And the reason why you might want to do this type of scaling is that you can trust the angle between these two rays. And when we get to more complex data sets, you'll start to see why that might or might not come in handy. Again, we only have 2 covariates here, so everything is just so simplified, it really doesn't matter all that much. So, but again, by doing that, which means that we want to be able to interpret this angle and the length of these arrows in regards to one another, to do that and project it onto the actual PC space, we are going to slightly distort the distances between 3 and 6 and 5 and 2 and 4 and 1 and so on. All of these distances among those fellas are being slightly distorted, so that way we can see with a very clear picture what's happening with M1 and M2. Scaling 2 is where the PC scores are scaled by the actual columns of our data, which M1 and M2. And this is usually the projection that we're interested in, because usually when we show a PC plot, we're really interested in showing how all these different individuals fall out in multivariate space. One thing I should mention here, because otherwise it might confuse people. As I mentioned, vegan was invented for plant ecology. And so that means that when you give it data, it is assuming that each row is a site and each column is a species. Here, each row is an individual and each column is a measurement. But as far as vegan, a package is concerned, it'll be referring to things as species scores and site scores. And the reason why it's doing that is because it's set up with the mindset that rows are sites, columns are species. Okay? Just to kind of put that out there so you're not confused by some of the wording. So again, if we do scaling 2, which is usually the one that you would probably want, and it is the default, if we look at a biplot of that, now we can trust the distances amongst all of our sites. And in this case, our sites are the individuals that we took those measurements on. But we can't necessarily trust the angle between the relative importance of M1 and M2 on either PC1 or PC1 or PC2. Okay? And in our case here, the distance is very, very subtle. That angle difference is very, very subtle. And you really don't appreciate the magnitude of the length of those arrows. Here, because we're only dealing with 2 things, these arrows are roughly the exact same length, whereas here, because we're rescaling it so that way we can preserve the distance between individuals, this has gotten to be slightly obtuse of an angle, and even M1 is noticeably a little bit shorter, or M2 is a little bit shorter than M1. So now our vectors that are describing the importance of M1 versus N2 are distorted, but we feel really good about the relative placement of the species that are out there. And again, this is the usual default that people use when showing these types of plots. It is indeed the default. And just to prove to you that it's nothing that you need to get too terribly concerned about, is that if we look at the scores, so here I'm extracting the scores using scaling 1, scaling 2, scaling 0, and then I'm also going to extract the scores when we use the PR comp function. So now I have all of these different scores, and they're all different, but they're all supposed to be telling us the same thing, right? But they're all clearly different from one another. The reason why it doesn't really matter too much is that if we were to look at the correlation amongst all of, and this is just for axis 1, but it would be the same for axis 2. If we were to look at the correlation of the scores, and remember the scores are the thing that we're plotting. If we were to look at the correlation of that, the correlation is perfect, right? It's a perfect correlation. It's just that they're on different scales, and that's just because they're trying to capture different pieces of the information. Oftentimes, people don't even show those rays anyways. And so then you would just use scaling 2, which, again, is going to be perfectly correlated with any other type of scaling. It's just all about how it looks when you're trying to interpret the data. Okay, so let's take a break for just a second. Hopefully we understand conceptually what a PCA is trying to do. We understand what the eigenvalue is telling us. It's going to be some measure of how much of the variation is being captured by each axis. And we understand what the eigenvector is, which is also called the loadings, which is telling us something about the importance of those different components as they correspond to each of the principal component axes. So let's take a quick break, and then we can resume. We're back. I promised it was going to be a quick break. Okay, so up to this point, we've been playing around with doing principal components analysis, and we've been really focusing in explicitly, or at least I hope I've been explicit, that we're really thinking about the covariance, right? Because that's what's being decomposed is the covariance matrix. Now, we've already talked about when we talked about covariance, that covariance is sensitive to units. And that can be a problem if we're doing a principal components analysis and we are allowing ourselves to be sensitive to the units. So oftentimes what people want is to do a principal components analysis on the correlation matrix. And remember, the correlation matrix is nothing more than simply the covariance of Z-transform data, right? And so this can become really important if the things that we're measuring that make up our data are measured in different units, right? Because again, covariance is sensitive to the units. And so if we were to look at the matrix that we've been playing with up to this point, is, that is the variance for M1, this is the variance for M2, and then this is the covariance between M1 and M2. And it's sensitive to those units. That is the matrix that behind the scenes, that PR comp or that RDA function was decomposing when it was coming up with our principal component axes. And so as a consequence, these numbers are going to be influenced by the units. So let's say hypothetically that M2 was in the units of inches, and we decided we wanted to convert it to centimeters because we realized that people would probably laugh at us in the scientific community if we were doing things measured in inches. So I'm going to go ahead and I'm going to transform that data. So I'm going to just create a new object where now I'm going to take that second column, right? Here's our second column. And let's pretend that's in inches. I want to turn that now into centimeters. So I just do the conversion of multiplying it by 2.54. And now we can look at the variance covariance matrix. And here again, that's the same variance that we got before because we haven't changed M1 at all. But now you can see that the variance for M2 is a much larger number. And it's a much larger number because centimeters are smaller, right? And so we got a lot more centimeters in there, and that's going to scale up. And now our variance is much larger. And similarly, the covariance has changed as well, right? Here's the original data. Here's our covariance. We only need to do one of those, they're the same. Here's the covariance, here's the variance. Once we convert M2 into units of centimeters, now here's the variance and here's the covariance. So the covariance matrix has changed because we've changed the units. And now let's do a principal components analysis now on that new data. And here we have it. Okay, we understand how to interpret all those things, but the first thing that should pop out at you is, remember when we did it on the original data, M1 dominated PC1. Now take a look. Now M2 is dominating PC1. And if we look at the summary here, even the amount of variation that's explained has slightly changed, right? Before it was like 72%, now it's 74%. And now PC1 is dominated by the second measurement, and PC2 is dominated by the first measurement. So everything has gotten upside down and backwards, right? If we were looking at our ordination on the original data that we were looking at, it's like, oh yeah, M1, that's where all the variation is. And that's what the first PC axis is capturing. And now when we've transformed that one little column of data, now it looks like M2 is super duper important compared to M1. And so this is the same problem that we had before when we were introducing ourselves to covariance, that it's going to be sensitive to the units. So usually what people want to do is they want to do a principal components analysis on the correlation matrix. Reminding ourselves again that the correlation is just simply the standardized covariance. It's the covariance of Z-transform data. And that'll put everything into the same units because it'll be in units of standard deviations. And so we won't have to worry about the problem of units. Now, there are some cases where you do want to do it on the covariance matrix, especially when all of your covariates are in the same units, because then maybe you are interested in capturing things that are actually, more variable in those units compared to other things. And so one place where you frequently see it done is in ordination of genomic type data, because all of the genomic data is going to be in the same units, and maybe you do want to capture those things that have a bigger variance compared to things that have a small variance. When we do it on the correlation matrix, everything is going to have a variance of 1, because everything's going to have a standard deviation of 1, and obviously 1 squared is 1. Math, right? And so usually, vast majority of the time, except for those of you that are going to jump deeply into genomic type analyses, you're going to probably want to do a principal components analysis on the covariance matrix. And so let's go ahead and do that. So one way that we could do that is to Z-transform our data, right? So again, oops, I hate it when it does that. Here's our original raw data. So again, this is back to being in units of inches, and I don't know what the heck that is. But one thing we could do is we could use the function scale as we have in the past. But this time, instead of saying scale equals false, we're going to just leave it as the default. And the default is to center the data and scale it, meaning it's going to center it around 0 and it's going to divide it by the standard deviation. And so now there we have it, right? There's our transform data. These are all in units of standard deviation. So again, that first guy right there is 0.387 standard deviations less than the mean, which again is going to be 0 because it's all Z transformed. And if we were to do a principal components analysis on that, again, that's going to be in units of standard deviations. Interestingly, because we only have 2 predictors, notice what's happening here with the loadings, right? Now they're both equally as important on each of those axes. There still is that negative correlation or covariance on PC1 between M1 and M2, but the actual loadings are equal. And again, in this case, they're equal because we're dealing with a bivariate plot, right? We're basically saying we're putting 2 lines through the data and it's all Z transformed and all has the same mean and the same standard deviation. So we basically just put a cross in the middle of a nice circular cloud of data. But again, we could do the same thing with the RDA function. Now you can see that the inertia is 2. Before, the inertia represented the total variance, which was 7.6 something. Here we're dealing with the Z-transform data, and we have 2 things. Both of those things have a standard deviation of 1, which means that their variance equals 1. 1 plus 1 equals 2, and so that's the total. And then we have the eigenvalues for the unconstrained analysis. Okay, so if we were to look at a summary of that, copy summary of that. Where am I? Okay, so now the first axis is explaining 58% of the variation, and the second axis is explaining 41% of the variation. So our interpretation when we look at those plots is going to be a lot different. When we did it on the covariance, it was 72% on the first axis and 28% on the second axis. But again, we knew that that was sensitive to the scale at which things were measured. Here, everybody's on the same playing field. We're doing it on the correlation matrix, and that's what we get, okay? Instead of z-transforming the data, the easier way, the recommended way that I would recommend doing it is just to tell the function itself that you want to scale it. And so in the PR comp function, all I had to do was say scale equals true, and that is going to automatically scale it. I'm going to fix this right now. Okay, so again, I'm taking my raw data, I'm putting it in there, but I'm going to say scale equals true. And that should look familiar. Remember, oh, it's symmetrical, and they have all the same values. And again, this weirdness is happening because we only have two things. If we had more than two things in there, then they wouldn't all be perfectly equal to one another. But you can see that it has converted it to standard deviations. If I were to sum those two things up, they would sum up to 2. But that's because the total variance that's in there is 2. And likewise, I will say if you use the PR comp function, notice that there's this little period after scale. That frustrates a lot of people when they're like, why isn't it working? And it's because there's that annoying little period there. In the RDA function, all we simply have to say is scale equals true. And again, that's telling the function that we want to do it on the correlation matrix instead of doing it on the covariance matrix. So I do that, and if I were to do a summary of that, okay, get the same values that we got before. Again, our loadings are slightly different, and they're not as perfectly symmetrical because it's scaling things. So that way, when we calculate these site scores, we get the ordination that we want. We can ordinate this. Let's plot that. And let's make that bigger so we can look at it. Okay, and so here, it is slightly different looking than what our principal components analysis based upon the covariance matrix. This was our principal components analysis based upon the covariance matrix. That is it based upon the correlation matrix. So these two guys that were up here in the corner, that is individuals 3 and 6. And now they're getting pulled down here. But again, that's because we've rescaled the variance. Originally, there was a much greater variance in M1 than there was in M2, but we've set them both on the same playing field as equals, and so now it's going to distort them slightly different. But again, that's because this is based on the correlation matrix, whereas the other analysis that we started with was based on the covariance matrix. But otherwise, we can interpret everything else similarly. Okay, so let's do this really quickly with something that might be a little bit more interesting, because right now we've been doing it with just two things. And I think that served its purpose, and the purpose there was to make it easy for us to understand what's happening and how we're interpreting things behind the scenes. But let's take a look at some real data. So these are indeed real data. It is in an object called wing morphometric biometry, and these are data of, guess it, yeah, butterfly wings. That's why I called it butter. It's these little handsome bugs. Oh man, I can't do that. Oh, I have to move that out of the way and then put that here. Nope, there we go. All right, let me move myself here. Yeah, so these two little butterflies right down there, very handsome animals. I've been paying attention to them for, 25 years. Just handsome little guys right there. And you'll note that on their wings, they have all these little dots and these little orangey thingies and little dots and little orangey thingies. These names aren't even right anymore because we found out that that is wrong. But we have different populations, and different populations look slightly differently, right? I mean, you can kind of eyeball that. Those are extreme differences from the variation you might see in a population. And so what we did in this little manuscript, if you will, is we measured a lot of elements from the hind wing of those butterflies. So we took the area of all these different dots that we have here. We also did some various length measurements from, the discal cell to the end of these veins, kind of the standard thing that entomologist types like to do with insects, which is measure a bunch of stuff. What can I say? Okay, so that's what these data are. They are actual real data. They're not data that I faked. That's kind of neat. And let's see how that data is set up. Let's take a quick look here at it. Head of butter. Head will just show the first 5, I think, or 7 lines of data, 6 lines of data. And so what do we have here in this? So this is the individual, and we're not going to really care about that right now. This is analogous to what our row names were with our silly example. And then we have what population they're from. There's going to be a handful of populations that they are from. And then we have all these measurements, right? H, CE3, C4, CL3, all the way through to X11, which are the different black dots. So we had all of these different measurements, and maybe we want to understand how that morphology varies across those populations. And instead of showing just a bunch of histograms of the height in CE3 and C4, we were like, hey, I got an idea. Why don't we do a principal components analysis on this and see if we can learn something about important elements of the variation, as well as be able to look at a pretty picture. And so what I'm going to do is I'm going to create an object called pops, which will be the populations, so we can just keep track of that. And then I'm going to create another object called B-wing, which is going to be columns 3 through 26, which is all the rest of the data, basically. So now we have all of our data, right? It's going to go all the way up to X11, and it's just the numeric data, and that's a lot of information from all of those handsome little butterflies. So I'll go ahead and I'm going to do this using the RDA function, just because it's handy. And RDA, yes. So I'm going to say I want to do it on the butterfly wings, and I'm going to say scale equals true, because I want to do it on the correlation matrix. And so I'm going to go ahead and I'm going to do that. And that's how quickly it did all that arithmetic for us, because it's a lot of math that's happening behind the scenes. So let's go ahead and look at a summary of that and see what we can learn. All right. So first, total inertia is 24. That's because there are 24 different columns in the data. And because this is on the correlation matrix, each column had a standard deviation of 1, which means that the variance was 1, because 1 squared equals 1. And so the total inertia is the total amount of variance that we are dealing with here. And now we can look at the eigenvalues and start to think about their relative contribution. Okay, so we start here with PC1. PC1 is 9.6, okay, which is 9.6 divided by 24 is 0.4, okay? So the first PC axis is going to explain 40% of the variation. That's pretty good, right? Because otherwise, if we had done just a bunch of correlation plots, each axis would only explain 1/24th. But now we're able to get 9.6 worth into one axis, and that's going to explain 40% of the variation. The second PC axis is explaining 18% of the variation. The third is explaining 6.5, and so on. But of all of that variation that we had, we're going to be able to show 58% of all of that variation just by looking at the first 2 PC axes, which is pretty good, actually. I'm pretty happy with that. We might learn something. Again, there's still a bit of the variation that we are not going to be showing in a pretty plot, but just shy of 60%, pretty good. oftentimes there's questions asked like, how many PC axes should I consider looking at? Because it's not uncommon in papers or in talks to see somebody plot PC1 versus PC2 and then maybe PC1 versus PC3. Because maybe you decide that, maybe this 6.5% of the variation is interesting enough to take a second look at it and see if any interesting patterns pop up. So one way that we can make that decision is to just say, well, PCA is a heuristic method and maybe I'm happy with 58%, or maybe I'm happy with 64%. If you want something that's perhaps a little bit more of an objective way to do that, you could be objectively subjective by looking at what is called a scree plot. And a scree plot is simply a plot that is going to plot out these eigenvalues. That's all the scree plot is going to do. So let's go ahead and look at a scree plot. And there's built-in function in vegan for scree plots, and there's our scree plot. Okay, so again, this is just the inertia of the first PC axis, second axis, third axis, fourth, fifth. So what people do with scree plots is they are looking for what is referred to as an elbow, which means that they are looking for a part of the scree plot where you're tumbling down, and then there's that little elbow there where you start to kind of level out. And so if I were to eyeball this, I would say, I'm pretty happy with maybe the first two axes. Because the fact that they're plateauing out, sure, PC3 might be explaining something interesting, but it's not that much better than PC4, which is not that much better than PC5, PC6, PC7, all the way through all the PC axes. And we can see that if we look at the eigen. I mean, you don't need to necessarily look at a scree plot. You can just kind of look at the numbers, right? It's like 40 to 8, or 0.4 to 0.18, that's a pretty big drop. 0.18 to 0.06, that's a pretty big drop. 0.06 to 0.05, not a very big drop. 0.057 to 0.048, not a very big drop. And none of these are very big drops after that. So the really big important drops are really happening PC1, PC2, and then, after that, PC3 is not that much better than PC4, which is not that much better than PC5, and, they're all kind of decreasing slowly. And again, notice that if you were to sum up all of those cumulative proportions, you will eventually explain all of the variation. But boy, poor PC24, that is only explaining 0.0006 is the proportion of the variation it's explaining. So 0.06% of the variation. So it's not terribly interesting. So again, you can look at the scree plot to make your decisions, or you can just look at these values here and be like, yeah, these are the two biggies, and the rest of these are kind of, they're slowly decreasing in the amount explained, but not terribly much. So okay, let's take a look at that. Let's look and see just what the data look like. I'm gonna make a biplot again, and jumping. It's a mess. And it is a mess. That's why I never use the biplot function. But here it says site 5, site 37. This is butterfly individual 37, butterfly individual 5. And they're all crowded here. And again, you can't even make out what's going on in there. But those are all of the arrows that are associated with each of our covariates. If we wanted to understand how those arrows related to one another, we would do scaling equals 1. And so now the relative positions of the butterflies themselves are slightly distorted, but now we can really trust these arrows. And so, it's crowded and it can be a pain, but when it's your own data, you'll figure out how to get exactly what you want out of it. But we can eyeball this and we can say, well, whatever H1 is, and I don't remember what H1 is. That's not even on there. So H1 is not very heavily loaded onto PC1, right? Because, the arrow stops there, and you can see its relative loading is really, really small, really close to 0. But it is pretty impressively correlated with PC2. Okay, so we know whatever H1 is, or HL, I think it's H1. No, it's HL. Whatever HL is describing, we know that PC2 is doing a good job at capturing the variation in HL, but PC1 is doing a poor job. If we look at one of these that are like almost at a 45-degree angle, like X10, right? So this is one of the dots on the wings. It's roughly equally loaded on PC1 and PC2. Okay, so that we understand how it varies, basically. Can also eyeball this and look at this. So if we look at X10, which is that dot, versus H, which is the wing height, they're both pretty strongly loaded onto both PC1 and PC2, but on PC1, X10 and H have opposite signs, meaning that on PC1, that's the components of their variation where they negatively correlate with one another in this case. Whereas on PC2, they're both weighted in the same direction. They're both positive. They're both positively, they are positively correlated with one another. And so again, those arrows are just a way to kind of understand how important the different covariates are for the different PC axes. And you could just as easily have gotten that information out of the actual object. If I went summary, okay, what were we playing with over there? We were playing with X, was it X10 or X11? I don't remember. I'm going to guess X10. And as predicted, they negatively covary on the first axis, right? And they both have the same signs on the second axis. So pretty much exactly what our plot said, right? Here's X10. On PC1, X10 is positive and H is negative. On PC2, they're both positive. And then I need to go back here. I want to look back here. And so you can use those arrows to think about which are the important ones that deserve a second look. Or we could just look at the numbers and look at the magnitude of the numbers. And you can see something like HL. Remember I said HL clearly wasn't very strongly correlated at all with PC1. And it certainly, it's not loaded onto PC1. And sure enough, its loading is 0.09, which is paltry compared to pretty much all the rest. Like HL is just not very good, but it is pretty substantially loaded onto PC2, whereas these other things like LB1 is not, right? So we can directly examine, and again, they're calling them species scores because of the historical legacy of what the vegan package was initially, the audience it was initially made for. But these are the column scores, and the other way you can think about that is this is our eigenvector. For PC1, this is our eigenvector, and these are the values that are associated with each of these different covariates. And we could go through across any of these axes and understand which one is more heavily weighted onto either of those PC axes. And so the other way that we can make our own pretty plot, because I really don't like those biplots. They're really good for like a quick look-see, but man, that's just some messy kind of wordy stuff. And I think you can customize them, but I've just never bothered learning, frankly, how to do it. Because I like to make my own plots, because, when in doubt, write more code, right? So what can we do? We can use that scores thing, and I can take the site scores, because that is what's part of that object. Here's the site scores. So these are the actual PC scores for site 1, and in this case, site 1 is actually butterfly 1. This is actually butterfly 2. This is actually butterfly 3. And so I can extract those scores by using the scores function. By default, the scores function will extract the first two PC scores, But you could, using an argument called choices, you could say I want 1 and 3, or I want 1, 2, and 3, and make a 3D plot out of it if you wanted to. These are all things that are under your power. Okay, so I'm going to start making a little bit of a pretty plot here. I'm going to extract those, and I'm going to say PCH equals 19 just because I like solid circles instead of the open circles that R usually does. So there's the plot of the data. Those are all my butterflies in PC space. And so now you might step back and say, well, that's neat. What am I supposed to do with that? And I would say that's a really good question. This is not supposed to be a Rorschach test. This is supposed to be something that's informative so we can understand the variation in these butterflies. So what I'm going to do is I'm going to color code each of those little dots for one of the 3 populations. Okay, and the populations we have here are L, C, and M, which refer to different locations. So how am I going to do that? Well, the little cheaty way that I do it, I'm sure that there's more elegant ways to do this, but I just create an empty object called culs. And then I'm going to say which of the pops, remember I created that object called pops, and this is what pops looks like. All those L's, all those C's, and all those M's. Those are the 3 different populations that these butterflies were taken from. I'm going to use this which function. I'm going to say which of those pops is super duper equal to L, and it's going to tell me 1 through 18. And so I'm then going to say, okay, for colors, where that is true, so for calls 1 through 18, that's going to equal blue. And then I'm going to do the same thing here for the ones that equal C. It's going to be all of those. So I'm going to say calls, all of those, they're going to be green. And I'm going to make those and the rest of them red. So now I can look at this plot. And I'm going to introduce this additional argument called cul. Where am I? Where am I? There I am. Ah, here I am. This additional argument called cul, which is going to tell R what color I would like all of those dots to be. And instead of just typing in a single color, you know, if I had done red, well, then they'd all be red. And granted, that maybe looks prettier than if they were all black, but it still tells me nothing. But if I put that vector of colors in there, because I've now created a vector called culs, which is identifying all those different populations as different colors. And so I'm going to put that in there, and then we can go to Fancy Town. Now we can see why PCA can be a useful way to look at the variation in your data, right? We started with a big matrix that had a bunch of columns and a bunch of numbers, and we wanted to understand, in a general sense, how are the butterfly wing patterns different among those populations? And so by putting it into principal component space and then coloring those points based upon the population, we can look at this and say, well, clearly population C is out here. Populations L and M are over here, and L and M do not appear to really be that different from one another, interestingly. But these green guys are definitely different, right? But now we can also remind ourselves, what axis are they different on? Well, they're different on PC1, right? I mean, clearly, if this is PC1 here, green is all over on this side, and the blue and reds are all over on this side. And then we can remind ourselves, because I have to remind ourselves right now, how much variation is being explained by that again? Was it 40%? Summary. Where am I? 40. Good memory, Jim. So clearly they're being spread apart pretty well by PC1, and then we just have to remind ourselves, and PC1 is what? 40% of the variation. PC2 is 18% of the variation. But if we look at PC2, and if we were to only look at PC2, there's no real separation that's that apparent between the green, the red, and the blue. They're kind of all occupying the same kind of place. There's no obvious break in the pattern. Whereas here, there is clearly an obvious break in the pattern. And so it might also then be a good idea if we were to say xlab equals, what is it going to equal? It's PC1. That's fine to say that. And we'll say 40%. We could do something that looks kind of like that. No, obviously we can't. Now we can. And I could say ylab equals PC2. And what was it, 18%? I hope it was. If it wasn't, you'll forgive me. I'm sure of it. And so, oh yeah, now that's good. And then, of course, you know, you could add a little legend over here to say which color corresponds to which population. If you wanted to get really fancy, you could get one of those pictures of those butterflies and put it up here. And, well, that'd probably start looking a little busy. But you get the point. You can start making a plot that would actually communicate to people. If I was giving a talk about this, I could say, hey, look at that. The green ones are different from the blue and the red. And people would be like, yeah, you know. Again, this is just a heuristic method. There's no hypothesis testing. But in principle, you could do hypothesis testing on it. And people do this. It's not wrong at all. It's just really important to remember what you're comparing when you do it. So let's say I wanted to know whether or not populations L and C were different from one another, okay? So we'll ignore the red dots for now because we're going to just do this as a t-test for just to make a point. So I could extract the scores for the first PC axis for L and for C as such, right? So I'm looking at the scores for PC1, and then I'm only going to keep the first 18 values, and I'm only going to keep the first column because that's PC1. So I could extract the scores, the PC scores for PC1, and then I could go ahead and I could do a t-test. There's nothing wrong with me doing a t-test, right? And look at that, it's significant. And then that's totally fine. Nothing we have done is naughty. But what we have to remind ourselves of is that yes, they are significantly different from one another for the 40% of the variation that the first PC axis is describing. And that's the important thing. If you choose to do statistical hypothesis testing using PC scores, again, there's nothing patently wrong with it, but just remind yourself exactly what you are analyzing when you're doing it. So I'm interested in whether or not L and C are different from one another. I'm doing a t-test here, and that t-test is significant, but it's significant for only the first 40% of the variation that is being explained, right, by PC1. And we could do it for, let's say, the third axis, right, which explained what, 6.8% of the variation. And we could go ahead and we could do that. And then I am going to do a t-test on that. And oh, they're not different on PC3. Recall that PC3, I think, explained what, 6.3% of the variation, something like that. Yeah, and so that's the thing to keep in mind if you're doing hypothesis testing using PC scores, or if you decide to use them as a predictor in a linear model. That is done quite often. There's nothing wrong with it at all. Just make sure that you are 100% fully aware of what you are doing with it. Okay, so that ends our coverage of principal components analysis and ends our introduction to multivariate techniques. Next time, we're going to talk about what you can do with distance matrices before we wrap up this part of multivariate. I know that there's a lot of moving parts to this, but I think if you play around with it a little bit, and maybe you have your own data that you can cook up, or maybe a friend of yours has data that you can play with in a principal component environment, just to get yourself comfortable with exactly what, what are these eigenvalues telling me, and how is it figuring out this percentage of the information that's being explained by the different axes, and what do these PC scores mean, and how do I interpret them, and what is the utility? I think once you get to that point, then a lot of the ordination, the multivariate type stuff that we won't be going over in this class will become a little bit, hopefully, more intuitive. Multivariate type stuff is used incredibly extensively, obviously, because a lot of our data sets are very, very multivariate. So this will wrap it up for principal components analysis. What we'll do next time in our introduction to kind of heuristic approaches to multivariate, and when I say that meaning that we haven't explicitly been doing any hypothesis testing. Sure, we did a t-test on a principal component scores, but that's different than actually doing multivariate hypothesis testing. We'll get to that at some point, but what we'll do next time is we will talk about ordination methods that use a distance matrix instead of simply a correlation matrix. So digest this stuff, have a little fun with it, tweak around a little bit with it, explore the webs, see if somebody else does a better job at explaining how to interpret those things than I do. If you find any great resources, let me know. I'm always happy to get better at trying to explain this in particular. Yeah, that's all. So enjoy sleeping on some multivariate stats, and I think that you'll find that you wake up with a smile on your face. Have a good evening or morning, depending on when you're watching this. Make sure to hit the like button. Don't. See ya. Bye.